Swami Gopalaswamy. I think I officially met Dr. Gopalaswamy last year at this conference when he was down visiting us, and it's been just a super enjoyable year over the last year to get to know him, work with him. The collaboration between the agency and the mechanical engineering department and all the folks they've brought in has been just a really exciting time for us. So with that, I'll bring up Dr. Gopalaswamy, Professor of Mechanical Engineering at Texas A&M University.
Thanks, Chris. Howdy. Good morning. So I'm going to talk about the safety initiative that's happening within Texas A&M as a prelude to this panel session that we're going to have on safety of autonomous vehicles. So we have programs, we're calling it CAST, Connected, Autonomous, and Safe Transportation Program. It's part of the RELIS Campus initiative that John Barton talked about previously. So this is kind of a stupid question in some sense. In this audience, you all know why are we working on connected autonomous vehicles, but I just want to kind of say that there are definitely several studies that have been done, which all point out the tremendous benefits that we get with autonomous vehicles. Definitely the number of lives saved, social benefits, the convenience of not having to be in traffic doing nothing, the number of crashes avoided, the number of the economic benefit, the environmental benefits by the fuel savings. The list goes on, and in fact, that's the reason we are all here. But before we go headlong into doing this, pursuing autonomous vehicles, we may want to step back and see, really, are we going too fast? Or what are the things we need to look at along with developing the technologies? So first, I want to look at today's automotive embedded software, what we already have on the roads. Safety is actually a growing concern for many automotive OEMs, even with traditional cars. We have a large code base that goes into many of our cars. We have 100 million lines of code that's there in many of our software. The complexity is growing. The number of ECUs, number of the functions that are there, the number of developers, the regions in which it's developed, the number of combination of features, the options that are offered, it's just mind-blowingly explosive in terms of the complexity. And there have been many headlines in the recent past of software-related failures. Whether it's really established as software-related failures or not, there are sufficient headlines. And the problems are all amplified dramatically when the impact of failures are on mechatronic systems where the machines, electronics, and human beings interact very closely, such as in automobiles. This is the background that we are talking about. And so the question is, when there are, obviously when you say software failures, we're talking about safety of the systems that are controlled by the software. So can we guarantee safety? For example, can we prove for sure that our system is safe? The reality is it's not possible today. It's too complex. We would like to have mathematical proofs to do that, but the reality is our mathematical proving capability is limited. People are working on that constantly, but we are very far from that. It's not going to happen. Not right away, not anytime near. Okay, can we test the heck out of the system and show that it is safe? In theory, it seems reasonable, but in reality, it's very impractical. If you want to talk about the number of miles that need to be driven in order to complete testing for an autonomous vehicle, it's in the hundreds of millions of miles of running, which is not practical. And this has to be done on a single version of the software. If you look at somebody like Google, they of course claim that they've run millions of miles on the autonomous vehicle, which is great, but it's not on the same single software version. The software has been evolving, and really we need to be able to test for a single version for hundreds of millions of miles to have even some reasonable statistical confidence in what we're doing. So yes, maybe we can do some level of testing, and we will talk about that here, which is to use mathematical models to do virtual simulation-based approaches. But really, it is a challenge. It's a big challenge. So what really can we do? Can we at least follow, quote unquote, industry best practices and say, hey, we are doing our best? Actually, that's really what we can do. And in fact, the industry is already kind of pushing towards it quite a bit. There are several types of, I use some buzzwords here, but really all of them kind of are very related: model-based systems engineering, ISO 26262 standards, requirements-driven development, architecture-driven development, simulation-based testing, blah, blah, blah. But the idea is they all say you need to use a mathematical model to model your system, take a systems view of the system that you're working on. That is, you go all the way from the requirements through a very systematic process to develop your controls, or to develop your algorithms. So the idea is that the safety is a challenge even in today's existing vehicles. So I just want to remind again, we are still talking about conventional vehicles. Now we say, how about autonomous vehicles? That's kind of just the context for why we need to really look at safety for autonomous vehicles. These systems are much, much more complex. We are getting new sensors. We are working with multiple sensors, so the complexity explodes exponentially. We are working with when I say we, I mean the automotive integrators have to work with new suppliers. There's going to be much more distributed development because the development is not going to happen with what's happening is when the automotive OEMs who are focused on just the conventional vehicles, the powertrain controls is very integrated. People can, there's much more very close coupled development. But as you start looking at ADAS and autonomous systems, more smart sensors and smart actuators coming into the place, which means development is happening in a much more distributed way with not exactly very, very tight communication, and that poses a whole bunch of challenges. And finally, there is this, for all the reasons that I mentioned in the previous slide, there's the safety mindset of the traditional automotive OEMs or automotive players, not just OEMs, automotive players. That needs to kind of get married with the fast innovation mindset of our robotic researchers who've been driving much of the development in the autonomous vehicles. These are all kind of the challenges that I think we need to look at. And then more technically, there's non-determinism that is inherent in autonomous vehicles. There are two major parts. Number one is we are replacing human decision-making with computer algorithms. That's a challenge. So there's non-determinism because we are figuring out how the driver should do things. I mean, today's driver is extremely adept. They're very, very adaptive in changing situations. We need to be able to capture that. We also need to figure out how the co-drivers, meaning the drivers in the neighboring vehicle, is going to behave. Yesterday, you might have seen Professor Langari's poster session on how we use game theoretic approaches to understand how decisions are going to be done by other people, but really it's an area of real research. And then pedestrians. How are pedestrians going to work? I mean, today we communicate with pedestrians through eye contact and other gestures in order to move forward. What happens when you have machines? So there are still a lot of areas where things are totally non-deterministic. And of course, machine learning is a critical part of what's been driving the growth of autonomous vehicles, because the systems are so complex. We say we don't want to understand the system. We'll let the learning algorithms understand and deal with that. No, I'm just kidding. But the idea is the machine learning really is also has its own challenges. The corner cases are way too many. Just a sample of pictures that I chose from somewhere, which talk about the challenges of machine vision in trying to understand the variety of scenarios that we may have to deal with. I'm sure Professor Murphy will talk more about this shortly. So with that background, let me quickly say what we are doing at Texas A&M. We have this initiative called the connected autonomous safe transportation program. The vision is to advance research and knowledge generation in the area of safety technologies for autonomous vehicle. We have seen the dramatic, incredible benefits that we get, societal, environmental, and economic benefits from autonomous vehicles that we all want to get. But in order for that to happen soon, we need to make sure that we can provide everybody the comfort of safety, the confidence in the technology, and that's really kind of where we want to spend our focus on. So, of course, we expect this to position Texas A&M as one of the globally premier research organizations in the area of autonomous vehicles with focus on safety. We plan to do that by leveraging the world-class expertise that we already have in transportation infrastructure technologies coming from TTI, the autonomous vehicle technologies coming from the College of Engineering, and of course the Raleigh campus, which is going to be a glue that essentially brings all these technologies together and focus on safety. With that vision, I just want to say this is a collaborative and system-wide initiative. It's, as you can see, there are some of the key people, or not key, some of the people here are in this picture. You can, I cannot point here, but on the left, you see John Barton and Ed Seymour representing the leadership from TTI and Raleigh campus, and we have Professor Darba, Professor Saripalli, who's here and who you probably met as you got the demo of the shuttle and the car. He's been taking the lead on those vehicles. Professor Ali Reza, who's from civil engineering, Professor Ratnam. So this, it's collaborative. There are some people missing here, Professor Des and other people from computer science, aerospace that we'll leverage as part of this initiative. The person that we will be missing, of course, will be Professor Carl Hedrick. John Barton mentioned he's the founding director of this initiative. He unfortunately passed away earlier this year, but we pledge to continue the vision that he has set forth for us. And what you see in the back are vehicles that we already have been instrumenting, making as autonomous vehicles. On the right-hand side, you have the F-150. It's, I think John Barton talked about it yesterday morning. It's led by Professor Langari. We have in the middle, the Kia Soul, which is led by Professor Ali Reza. And then on the left, we have the MKZ Lincoln, which is led by Professor Saripalli. In fact, that picture was taken right at the beginning, and now we kind of wrapped it and make it look nicer. But the point is, the way we are developing this center activities is to building up what we call as the high visibility technology demonstrator platforms. So these cars, for example, are examples of those platforms. These would be large-scale demonstrator platforms which would then anchor specific research projects that then would address very deep specific questions. And they will also serve as learning platforms, and the focus would be on safety characterization, analysis, and development of innovation to support autonomous safe vehicles. So just to wrap it up with how we are doing this right now, where we are right now. As I said, if you look at how we prove or demonstrate safety, proving safety is a little bit further out. We will, of course, work on that. But more urgent would be the ability to do a variety of testing. And we want to do that in a way a little bit different than what's being adopted today. You have on the one extreme the Google approach, which is extensive in-road testing in mostly uncontrolled environment. As I said, they've driven millions of miles, but statistically speaking, if you want to look at human beings, we hear you need hundreds of millions of miles, if not billions. That's one extreme. The other extreme is the Tesla approach, where you kind of, it's over-the-air kind of download of your latest improvements, and hopefully things will work out. And we are thinking we'll kind of go somewhere in between. We want to take a more systematic approach through several technology demonstrator platforms. The first one is what we call as the Virtual Autonomous Vehicle System Technology Demonstrator Platform, or VAVS TDP for short. Essentially, it is a completely virtual environment that captures the vehicle dynamics, the sensors, the environment, the scenarios, perhaps the human driver interaction, and do a very extensive testing in a virtual environment. And here, our idea is not to just test one vehicle, but an entire ecosystem of vehicles that consists of perhaps a few miles of traffic with hundreds of cars. So this is something that we are working on. So that's our first TDP. After that, we want to move to slightly more real physical hardware, but in a very tightly controlled environment. So these are what we call as the autonomous vehicle scaled indoor technology. These are really 1/10 scale cars, remote controlled cars, but they have the right kind of processing power like a real car, the same kind of sensors, and we build mock-up cities inside the lab and do the evaluations there. This also serves as a great learning platform for the students. Then we have what we call the dedicated lane, low-speed autonomous vehicle technology demonstrator platform. In fact, in other words, golf cart. You've seen this outside, and this is really kind of helps us transition from the scale cars into the outside world. And this kind of addresses different types of scenarios, high-density pedestrian traffic, for example, and things of that nature. Then, of course, we have the regular research autonomous vehicle TDPs. You've seen the truck platooning project that we are doing as a part of the TTI-led effort. We also have the other cars there that I just talked about. And finally, the most important thing is to bring this all together. The RELIS campus will serve as the glue where we will do a smart city infrastructure to evaluate advanced innovations in the autonomous driving and connected area. And all this with the idea that we will try to demonstrate safety, enhance safety, and the way the architecture of everything would be set up is that the algorithms that you develop in the virtual platform can be seamlessly transferred, or almost nearly seamlessly transferred, all the way down to the vehicle. And that's kind of the approach that we're taking. So that's kind of a quick overview of the safety initiative that's happening within the College of Engineering. Now, what I would like to do is we have a very distinguished panel of speakers whom we would like to hear from on safety. I would like to introduce them. Roger Berg. Roger Berg is Vice President of Denso's North American R&D group. He is responsible for Denso's regional research and development of connected vehicles, automation, and cybersecurity at their laboratories in both California and Michigan. He also coordinates closely with Denso's research and product groups in sister organizations located in the US, Japan, Germany, and China. Borg has experience in military, consumer, and automotive electronics from previous engineering and executive positions in Northrop Grumman, Motorola, Sony, combined with his 15 years at Denso. Berg earned a Bachelor of Science degree in Electrical Engineering from the University of Illinois in Urbana, Illinois, and a Master of Science in Electrical Engineering from Illinois Institute of Technology in Chicago. He is the inventor or co-inventor on 8 US and international patents. He is a longstanding member of the SAE and IEEE and sits on the US DART's ITS Policy Advisory Committee. Please welcome Roger Berg.
So, good morning, everyone. I'd like to thank Texas Transportation Institute, Texas A&M University, and Professor Gopalswamy for the opportunity to participate in this, convention of thought leaders in the area of transportation, transportation safety, and mobility enhancement. I usually do what I'm asked according to my boss, usually, not all the time. So I have been asked to talk about Tier 1 automotive parts suppliers' perspective on automated drive safety today. So I'll try to do that for all of you. So first, a little bit about Denso. Even in a transportation conference like this, not everyone knows who Denso is. We are a Tier 1 global automotive parts supplier. According to Automotive News, the second-ranked supplier in the world. We have about $40 billion in revenue each year, and employ around 150,000 employees on a global basis. In North America, we have 28 facilities around the country, mostly manufacturing for the localized automotive manufacturers. But we do have an extended amount of research and development, primarily in the area of intelligent vehicles, smart vehicles that deal with automated drive, connectivity, and cybersecurity. We have 3 centers of research and development, one in Silicon Valley, like everyone now. We have another which deals mainly in software, technology, and corporate ventures. We have another facility in San Diego where I'm staged, I guess, which deals mainly with connectivity and researching connectivity in smart vehicles. And then our regional headquarters in Detroit, which deals mainly with the integration of all these kinds of software and hardware technologies to do safety and intelligent vehicles. So really, as a company, our really long-term global policy has to do with protecting lives and preserving the planet. So we have the kind of pillars of our research and development and product development, actually, that focus around confidence and safety and global environmental preservation. So today I want to talk about the kind of confidence and safety that our products involve. So our concept of a driver assistance and safety and automated vehicles revolves around what we call everyday confidence and extraordinary safety. If you think about the normal driving environment, really you don't get into crashes and collisions, thankfully, every day. So one of the areas we focus on is this kind of concept of everyday confidence. So our products and our systems, we are specifically designed to assist in the perception and judgment and operation of everyday driving, which is not necessarily hazardous. But then on these hopefully very rare occasions when you do get into a condition where you might engage in a collision, our systems are designed and developed and integrated to reduce the impact of a collision. And in the case of that one happens, it's how to react afterwards. So really, it's the kind of the idea of ordinary operation, but also to assist you when you do have a collision. So in order to do this, we take a kind of a holistic approach that involves not just the vehicle operation itself, but also how the human interfaces with the machine, so to speak, and how the human and the machine interact with the environment upon which the transportation system rides. So really, we want to take not just a single approach in any one of these areas, but actually a kind of a holistic view. So let's first talk about the vehicle system. And when people talk about ADAS or automated vehicles, this is generally the area in which they kind of focus their efforts. It has to do with the driving environment recognition and the actuation of behavior of the machine itself. So Denso has a wide-ranging product portfolio dealing with active safety, ADAS and automated driving. Includes all the traditional sensor and perception devices, including radars, LiDARs, cameras, ultrasound. We also include things that sense not just the outside of the vehicle, but also the driver's status, so driver status monitor, how the human operates with the machine, in addition to how the machine operates itself. And most recently, we've attached what we call a connectivity, so that the sensor and the perception network is not necessarily just on the vehicle itself, but also relies on sensors and perception network remote from the vehicle. And then we talk about vehicle motion control, DENSO does things like electronic power steering systems to actuate the activity of the vehicle after the perception. And then, as I mentioned, in the case where a collision is inevitable, we also have some passive safety components that assist in the collision itself or after the collision. So kind of the second component of our, universal approach to automotive safety is in the human-machine interface area. In this case, we do a lot of collection on how users or drivers or whatever, operators or passengers in this case, how they behave and how the machine and the human driver interact. We take that data and then perform some analysis and modeling to how people, kind of the social and mechanical kind of perception and reaction to how the driver or the operator actually works with the vehicle. And then we design systems to kind of manifest that in the way that the holistic system approach, where the driver is actually part of the feedback system, is part of the way we analyze how the vehicle safety system works. And we use that in this holistic approach to how drivers and vehicles react. And really that's, as we talk about the different levels of automation, from essentially zero automation where the driver's in full control to fully automated where the driver is not in any control and the vehicle itself is in control, there's a kind of a spectrum of different involvements of how the human and the machine interact. And we have to design our systems with respect to that kind of holistic approach. And it's quite difficult, as you might imagine, difficult and complicated, and it takes a lot of analysis and modeling and trial and error and prototyping to get things right. Thirdly, let's focus on what we call the information and communication area, which is really the perception of the region around the immediate vehicle. So here we use connectivity to kind of extend the area of perception, not just in the immediate vicinity of the neighboring vehicles where the traditional perception engines kind of work, but we've now thought about extending that concept to even remotely censored devices and vehicles, and really the transportation system in which the automated vehicles and kind of the heterogeneous level of some automations, some fully automated, some non-automated at all, and how those different agents or entities work together in terms of the transportation system. So we have done a lot of research and development on connectivity and how it relates to the kind of the connected safety of automated vehicles, and done a global level of research in this area, including the first start of production of V2V related systems in Japan. So not only I want to talk about PowerPoints and how our kind of theoretical approach, but we also actually have performed the prototyping and demonstration of these technologies in a number of venues. I want to review a little bit about what we did in Detroit a couple of years ago. So one of our demonstrations had to do with the what we call advanced HMI and cockpit management. I tried to illustrate how important we thought the kind of concept behind the human-machine interface is in the safety of semi and fully automated vehicles, even to the extent where a highly automated vehicle will take you from point A to point B. There's still actually some human-machine interface in hailing the vehicle to come and get you and telling it where to go and things like that. So we think HMI is really important even in the area of highly automated vehicles. So we did some demonstrations that really talked about how connectivity really fits in with the idea of the kind of cohesive concept of human-machine interface, even to the extent where the broad-end device like a cellular telephone might assist the driver in the perception of their surroundings and the kind of awareness. The second was talked about a demonstration where we actually did, in essence, a kind of light vehicle platooning system, but not really. In this case, all we used was GNSS, or global positioning, and inter-vehicle communications. And we had a lead vehicle essentially set down a continuous pattern of waypoints and had another vehicle follow without the aid of any radars or cameras or LiDARs or any kind of onboard sensing, only remote sensing in terms of the GPS and the vehicle-to-vehicle communication. And we can follow around in any kind of pattern that you might imagine, even at high speed. The third was what has been already talked about here at Texas A&M about highway truck platooning. We did a demonstration on live highways, freeways in the Detroit metro area, where we only used longitudinal control to in essence, enhance a cooperative automated, what do they call that? CACC, ACC. Anyways, you know what I mean. And it's actually quite interesting to be in the rear vehicle where all you see is the back end of a trailer, which we're operating only like 26 feet away, and all you can see is the back end of a trailer. And when you feel that the truck in front performs this kind of emergency braking scenario, it almost feels like that truck is driving yours, because you can feel the deceleration even before the brake lights turn on. It's quite interesting. Hopefully I'll be able to show you. Were we able to play this, Ben? Okay, thanks. So so here's a little film clip of our demonstrations. Hopefully, yeah. Denso's really looking at forward-level technology. So this is kind of thing that changes the way people drive their cars, and that's really exciting to be part of. A little less gray, a little lighter.
Looking at it from a big picture, just with radar, with cameras, you get to see what's right in front of you. With V2V, you get information about all the cars around you. So imagine having a large map around you, with knowing where each and every vehicle around you is.
In one of the demonstrations we're doing here at the World Congress, we have essentially connected automation. What I mean by that is the following car just does whatever the lead car does without the driver even steering or braking.
The Denso's future is to take things like the SRC, which we're leaders in development of, and we're employing those in our system to give us the automated driving capability.
More and more technology is coming to the vehicle, from the consumer electronics side, from other components as well. How do we manage all this information that's coming to the vehicle that was never there before? The HMI with the situational awareness and the added safety features, that logic is it's pretty close. A lot of people are looking into it, but the implementation is the most important part of that, which Denso is working on.
Danger ahead. Pedestrian is distracted by calling on the left.
Platooning technology is just one aspect of vehicle-to-vehicle technologies that we see being deployed in the future. With a following distance of 40 feet between the two vehicles, we're able to remove the aerodynamic wash from the back trailer of the front truck They are achieving a 5% fuel economy improvement, while the rear truck with the aerodynamics and the closed following distance is receiving 10%. Not only are we realizing fuel economy improvements, but it's also a safety feature because this technology is integrated with the collision mitigation and safety systems surrounding the brakes on the vehicle.
We have a team dedicated to HMI development. We have a team that's dedicated to the V2X development as well, and being able to combine both teams and come up with the right mix for an autonomous car. Denso has all the components and the know-how to do that.
We can introduce this now with some of the large fleets and then roll that into OEM where it becomes standard installation in the future.
Just as more cars start to get this installed in it, just imagine the possibilities of how much more intelligent we can make these vehicles.
This is really cool stuff. It's kind of like if you think into the future, everyone will think, oh, why didn't we have this before?
So by doing these demonstrations and pilot programs, you learn so much more than by just thinking about it in the laboratory. In closing, I want to just kind of give you our Denso's vision of our approach to automated driving, and it's kind of a gradual one. So today we see various levels of automated driving capability or ADAS extensions to the driver's capability by using the machine and its sensing and actuation. We see this moving to more of a mobility lifestyle where kind of all drivers enjoy this kind of confidence, convenience, and safety that ADAS and automated driving can provide. And eventually we lead to an evolution of lifestyle, whereas people don't even think about driving anymore. They just will either call, hail a automated taxi cab or a fleet vehicle to take you from your home to shopping and back, or home to the movies and back, or even to work or school or whatever. So it's really kind of an evolution of lifestyle as it relates to active and safe transportation. So thank you very much.
That was very impressive. Really impressive to see the progress and the breadth of what Denso can do. Now I would like to introduce the second speaker. Can I have my presentation back? Just pass the slide. Okay. So now I'm very pleased to invite Professor Robin Murphy. I want to show the TEDx, she's a TED speaker, as you can see. That's the point there. So Robin Murphy is a Raytheon Professor of Computer Science and Engineering at Texas A&M University and Director of the Teach Center for Robot-Assisted Search and Rescue. She has over 150 publications on artificial intelligence for robots, including Introduction to AI Robotics and the award-winning Disaster Robotics, an IEEE Fellow, a TED speaker, and founder of Roboticists Without Borders. She has deployed ground, air, and marine robots to over 24 disasters in 5 countries, including the 9/11 World Trade Center, Katrina, and Fukushima. Professor Murphy, thanks very much.
Well, howdy, and thank you for having me here. And with a name like Murphy, I always have last-minute things go wrong, so we'll see what happens with my presentation. So I'm going to be talking about human-robot interaction, and in particular, the idea of safety of intended functionality. And just a little bit about me is that I do work in autonomy. I am a professor of computer science who works in artificial intelligence applied to robotics. I have a textbook, the second edition will be coming out this year, And also, I do a lot of government service and co-chair the Defense Science Board study on the role of autonomy for Department of Defense systems. And what may be even more interesting is that besides me writing books, books have been written about me. And so in the Joint Cognitive Systems work, there's a Robin Murphy's Law that says that any robotic system that gets deployed with whatever level of autonomy it started out with, it'll be at least one level lower in the field, because the world's just much harder than we always think it is when we actually put things in the field from the lab. But with that said, so why would I be here? I mean, Director of Center for Robot Assisted Search and Rescue. That seems, are we expecting to have disasters with vehicles or things like that? No. But my work started in human-robot interaction in the late 90s, because what we started to find as we deployed these robots, these are robots that were built mostly for sewage pipe inspection, military, they're hardened, they're commercial, and they were failing in the field. And what was the source of failures? 51% of the time in these disasters that they're failing were ascribed to human error. So you're not going to get a huge improvement by improving the power systems or making the battery system better. You've got to make the human side of this, the human-robot interaction. And so we started that work and helped co-found the field of human-robot interaction. So when you think about the safety of intended functionality, so for us in computer science, particularly in AI, we were amazed that Tesla got away on the lawsuit on the death. And that is because the idea that you have a person and you're going to say, oh, well, and if it doesn't work, we throw it back to the human. And the cognitive engineers have known for years, since the late 60s, Christopher Wicken's work was the first to really start looking at that, is that doesn't work. And certainly in my own field, we see, oh, the UAV's fine. We're going to use it for a disaster. We're going to use it for inspection. We're going to drop off stuff to people. We're going to be flying what we affectionately called a flying weed whacker of death next to somebody's head, and then something's going to go wrong, and then it's the pilot's problem. We're going to punch little little things around, and then, oh, look, it's your problem now. Oh, how do you like that? And unlike other types of aircraft, you've got maybe 8 seconds to recover. And good luck with that, because your brain, your neural paths don't work that fast. You can't actually respond to some of these things. And so the same thing we see with the Tesla, that was a big concern for us. And we know in software and autonomy that it's not just nothing works perfectly in the manufacture of the vision systems. It's not going to work perfectly. How do we get that trade-off between human and machine? And this is an area of concern for us. So why is this a major human-robot interaction, a major concern? So they ask in the panel, what's the #1 challenge? And so I'm arguing the #1 challenge is HRI. And there are 2 reasons. First off, automated vehicles is brand new. It's a formative field. Already on the presentations we've heard, it's not clear which features are going to be the ones that are going to stick, that are going to be the ones that are the best, that are going to be the ones the consumer wants, that are going to be the ones that the transportation industry wants. So we don't know what that is. So it's still formative. We're still at that early phase on crossing the chasm. And it's innovative. The technology is changing so fast, which is why I love being at a university. Look at all the changes that have happened in the last 18 months. And then that translates into manufacturing. So the diffusion of innovation says that it's somewhere between 7 and 20 years before a system settles out. You know exactly, the technology's hard, and you know exactly how it's going to be used. We've got all the workflows. People are comfortable with it. And if we wait that long, which is when the traditional human factors work kicks in after things have settled out, then we have huge investment in possibly incorrect systems and systems that we've invested so heavily in that we can't fix later on. Another reason why human-robot interaction is so tough, it's hard to test. And this is an eye chart, and it gives you an idea. Here are all the different metrics for human-robot interaction that have been proposed by researchers from NASA on down in human-robot interaction. Most of these are impossible to test. You can't, they would be great to know, but you just can't. How are you going to do it? Most of them required, the ones that you can test for are things like SIGA. They require you to interrupt the workflow. They require you to do something intrusive. That makes it really hard. And particularly, how do you do it when you don't? You've got that innovative, formative. How do you project forward? How do you anticipate problems rather than say, yeah, that screwed up. That interface, yeah, that wasn't so good after all. So that's a big challenge for us, is that how do you test in a way that's reasonable? Well, fortunately, we're not really starting from zero. I mean, this has got some similarities, on the cognitive side to the aircraft industry, and in particular, the introduction of the autopilot. Okay, and what they learned from the autopilot was they gave the autopilot to pilots. They threw it out there, and they started having crashes. Okay, great. Okay, it turned out because the autopilot would be fine for perfectly modeled situations, and then the moment that it got out of where it was the control it could handle, it just turned itself off. And the pilot was told, you're supposed to watch the autopilot and take over when it happens, right? And they couldn't do it, right? Because by definition, the autopilot's got all the normal cases and is going to fail or turn itself off, and the non-normal conditions, which would be hard even if you were paying attention, and you're going from whatever you were doing over to that. And the pilots were making huge mistakes. And now they do things like, as it starts to get within 2 standard deviations of normal, begins to shake the throttle, the stick, begins to make little audible noises and things like that to give the driver's warning, so that the pilot's warning, so you don't shift out in there. And so they came up with a whole set of similar things like that, unsafe acts and preconditions for human errors that now you have to check off. They're still very vague, but you can at least have a checklist to look at. And they also have done like fundamental research. We've already talked about the human out-of-the-loop control problem, but also the visual separation of display screens, that what we found with the pilots, with the fighter pilots, they were beginning to, we're running out of display space, so we're gonna put stuff here, we're gonna put stuff there, you're gonna be typing in there. And it actually caused performance to go down, which is why we had to have all those Top Gun schools, which then led to the really great Top Gun movie and the good soundtrack. But it was a problem in terms of engineering, and again, it was the DARPA program that came in with the Pilot Associate had to go back and fix those problems, because it was like, let's give them more displays and this and this. It's like, well, first off, when is it a good idea to do this? Okay, probably not, in retrospect. And so can we leverage what we know and apply those? And so as we go forward, though, we're not starting from zero, but we still have some differences between planes and cars. So when you have a problem flying a plane, the problems are usually plane-centric, like the 800 Airbus that went down over the Canary Islands. It's got de-icing. You're not fixing to hit anything. You can't see the wind. You can't see the conditions, really. But what you've got to do is infer what's going on with your wings, why things aren't working. Now, if you're with the cars, it's less about the cars, and it's more about the environment. Right? What the heck is happening out there? Like with the Tesla, okay, the truck now looks like it's the sky, this and this. I, the driver, have to disambiguate what's going on. So that's a problem. Another challenge is that the pilots and the drivers are different. I mean, just think about the difference in training, what you expect even of a civilian pilot, for a private pilot's license is hugely different. I mean, come on, theoretically we have driver's license in the United States, but you've been in cases where you don't really believe that, right? Because of, what we've seen. We also have a different expectation of consumer products. I mean, the stuff that pilots will put up with automation, customers not going to do, right? They're just not, it's not, pilots will put up with a lot of things that are inconvenient and will be trained around, but I wouldn't accept that in my car. I don't understand. I like iPhones. I want it to work now, okay? It works for me. And then I think the level of and the opportunity for distractions are much higher. I mean, the pilots, we've had cases where they kind of overshot an airport because they were filling in forms and stuff, but that's way different than dealing with the kids. You've got a little beepy thing, you've got your music's playing, all these different things going on, and things that you're going to be, as soon as I get an autonomous car, I'm going to be like doing talks and grading papers. And so, how is that going to work? If we try, again, back to that human out-of-the-loop control, how are we going to do it? It's a very different one than a pilot. So let me just conclude with a little bit of work about what we're doing here in our program in my group. And so we're focusing with funding from the National Science Foundation on projective test methods to anticipate HRI methods. So instead of trying to test in quality on our HRI, test in safety at the end, let's see if we can project from day one, even when we're at it, TRL1, this is a pie-in-the-sky idea. Can we start immediately seeing what we need to do so that we can get provably correct and trustworthy interfaces? And then we've got looking at the non-disruptive into observation methods. So for me, going to so many disasters, it's not a classic study where you can wire people up and put electrodes and you can control them and do repeatability. How do you exploit the fact that you're now having prototypes out there? You want to start learning as you go from what people are doing, both your own test drivers and people who are the early adopters, without trying to wire them up or do like say, oh, stop and fill in this 10-page survey. Yeah, that'll happen. Okay, so these are the things that we're working on, and we'd be delighted to work with you. And of course, it's a delight to be here to learn from you and see the challenges, because that's going to improve robots, vehicles, unmanned systems all over of all different kinds, because it's really the same problems. Thank you.
Thank you, Professor Murphy. It was a wonderful perspective. Next, I'll invite Ahmed Mahmood. I think I was presumptuous to talk about what the OEMs think, and so I'll be okay if you completely shatter me. But let me just introduce him. I have actually a newer introduction than this one, so I'm going to use that one. So Ahmed Mahmood, CIO, Global Manufacturing, Global Purchasing and Supply Chain, Customer Care, and After Sales and Quality, is responsible for transforming the organization into a highly in-sourced team with a focus on innovation to drive value into GM. He also serves as GM's executive champion for Texas A&M University. Mahmood is a proven change agent at the senior executive level with an innate talent for attracting high-performance management teams. He has more than 25 years leading teams in enterprise-level information and technology. Prior to joining General Motors in 2012, he served as Senior Vice President of Hewlett-Packard's HP.com, e-commerce, and marketing organizations. Prior to HP, Mahmood was Senior Vice President and Chief Information Officer of AMD, where he was responsible for managing the company's global technology strategy, assets, and infrastructure to best meet internal needs and serve AMD's customers. Mahmood spent many years at Dell Inc., where he served as Vice President of IT in supply chain, manufacturing, e-commerce, and other roles. He also held various IT leadership positions at Eastman Kodak Company. Ahmed Mahmood is a recognized IT industry leader. He was named to Computer World's Premier 100 IT Leaders in 2009 and has spoken at the Aspen Institute, among other conferences. He also is a University of Texas Senior Service College Fellow, UT McComb School of Business VIP speaker, and a member of the Texas A&M University College of Science Advisory Board. He earned both a bachelor's and master's degree in physics from Texas A&M University and lives in Austin, Texas. Please welcome.
Well, thank you very much. One of the things to learn is to always ask to be on the first day, because when you're on the second or third day, you look at everybody else's deck and say, we need to do like just-in-time deck changes because everybody else has great speeches and great pictures and topics, so you want to change it up a bit. So I wanted to change the way I'm presenting in a way and take advantage that I'm at a great research institution and sort of share quickly what the initial topics, but I wanted to also end it up on research ideas. And I'm going to focus on ideas that I find what I call not very sexy, but are fundamental to getting the work done. So one of the things here in the first picture, that's Mary Barr, our CEO, with our autonomous vehicle. And one of the things that I do with this picture, and then there'll be more, is all the fancy stuff on the car, right? Everybody has seen that. And there's a reason I want to focus on that. Because other OEMs, you notice, have decided, wait a minute, we're just going to use visual. These have visual cameras. I can't count the number of cameras it has. It has radar, ultrasound, LiDAR, you name it, it has it. And some of the conversations we talked about before, and you're saying to yourself, wow, that's a lot of stuff. Why? It's because exactly what you were talking about earlier, it's none of those systems are perfect. Vision is great, it's not perfect. LiDAR is great, it's not perfect. Radar is great, it's not perfect. So the reason an OEM puts all that stuff there, it's not because we want to create more complexity. It's to deal with the fact that we need this complexity now, and this hits right where this conference is because vehicle-to-vehicle communication is not completely there, barely. Vehicle-to-infrastructure is not there. We need it. Vehicle-to-pedestrian, on and on. All these things are not there yet, so therefore, we need to have these fancy gadgets that cost a lot of money, right? So just keep that in the back of your mind of what are the OEMs doing. The OEMs are doing stuff to add a certain level of complexity, but that is needed at the moment. Over time, my expectation is the complexity will be reduced as some of this technology surrounding it. If every single car can communicate with us, we'll be able to ease that. One of the things with my role is I get to see, and the main purpose of this picture is I get to deal with the procuring the parts, building the parts, the quality of the parts, and then I'm also working with the teams to fix the cars after the fact, right? And you'll notice we understand the complexity, right? We understand the complexity, so the initial set of what the OEMs are doing, you notice we're not talking about the initial releases being to the consumer, you go to a dealership and buy it. And, we're not talking about where you can go to your local dealership to get it fixed. We're talking about we're going to own the vehicles, we're going to run it in fleets, we're going to do certain things, and I'm going to talk about that because we want to control the technology, we want to deal with that level of complexity because we're not underestimating the complexities, all right? Now, what the other thing that I wanted to sort of hit upon a little bit is this picture right here. What I'm trying to say here is some of the technology that's being used in autonomous and safety is not, we're not worried about the safety for the future in autonomous, we worry about safety in the vehicles we have today. So some of the new cars we have has a warning, rear seat reminder, look in the rear seat because there's been incidents with people left babies in the rear seat, right? So this lane, you're going on the lane, how many people have the cars where every time you leave the lane, it sort of shakes? Mine goes nonstop. I think I'm the guy that goes there and I need to change that motor on a regular basis, but that's something that has been going on for years, right? So some of this technology, some people are saying some of this technology, it's sort of, we are building on the technology with our tier 1 partners and so on over many, 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 many years. It's not as if everything is brand new. We're building upon it. And things that we're building on is stuff in the vehicles you buy today. And, the statement that, if you want to see a future of what is the next generation of some of this stuff, Cadillac is usually where we put most of the stuff. And some of the interesting things, like I have a Cadillac, and it, you know, it shows you when a person is walking on the side of the road. And it shows you, puts a little green square on it, and you see it. It actually has night vision, so it puts a little square there. You know, that's the same technology that the autonomous vehicles is identifying people and so on. So that technology is being added now and is being used for multiple years. So when it goes into the autonomous vehicle, it's not the first time there, it's there for a while. So I'm going to go through these quickly because then I want to sort of focus on the challenges. So we're releasing the CT6 this year with Super Cruise. And this is not a beta, this is not a test. This is the next generation of cruise control, right? Is it fully autonomous? No. Just like adaptive cruise, if you remember, the car in front of you slow down, you slow down. This one is on the highway, it'll keep you on the lane and will stay there. It will not do lane changes. So we're gonna learn from that. What are we learning from this? We're learning things like, wait a minute, we need better maps. We cannot just depend on the maps that we're getting from a year ago or 2 years ago when we got the update. We need to worry about, wait a minute, this exit is closed. How do we communicate to the next Cadillac that this exit is closed or not? Can we do that kind of stuff? So this Super Cruise is the next generation of cruise control, and we will learn from those capabilities and be able to take advantage of vehicle-to-vehicle communication. Now, as we know, vehicle-to-vehicle communication, some standards have come out on, you know, the ciphers between us so that we know that this other car is who it says it is. That's the first step in cybersecurity that we need to worry about. So cybersecurity is critical. We need to make sure we carry that on. And now there's the next generation, right? Vehicle to infrastructure. I think that's the piece that everybody's hoping for. That will reduce the level of complexities. Because if the infrastructure tells me I'm a red light, I'm a green light, I don't need super duper fancy gadget to say, ooh, what light is that? I'm a stop sign. But it's not there, so these vehicles need to be aware of it. But that's why you'll notice the first implementation of these autonomous vehicles is not going to be autonomous vehicles across the country. It's going to be in a very controlled environment. It is Manhattan. It is San Francisco, in this area. There's a reason for that. What is the processing capabilities of LiDAR, radar, all this stuff being able to communicate? I mean, these vehicles are what? These vehicles are moving data centers. Does anybody want to guess, you know, what is the speed currently for all these vehicles that people are probably with the first release is going to be? Right, between 30 and 40 miles an hour. Not 70, 80 miles an hour for fully autonomous vehicles. As processing improves, as data improves, so that's a controlled environment. This is, OEMs are very, very aware of safety and so on. So we need to say, what is the environment that this is going to work very well in? Versus saying, oh, we have an autonomous vehicle, let me take it from New York to San Francisco and see what happens. Right? And here, some of this stuff you see, vehicle to passenger, this is stuff I'm seeing today in my CT6, which is pretty cool, actually. I mean, it has this night vision. Any hunters here? You know, this is a little bit of a joke, but I'm sitting there. The first time I saw this night vision stuff, I'm saying, man, this would be perfect for hog hunting. But having a CT6 I hope this is not recorded. Delete that part. but you can see this stuff today, right? We don't need to wait for autonomous vehicles, and we will learn from that. And it's pretty interesting. I'm going through my neighborhood, and all of a sudden, I'm driving, and all of a sudden saying, pedestrian detected. And if it's at night, and all of a sudden I see a pedestrian detected, you can see the pedestrian and a little, squares on it. That's pretty cool for me. Interesting thing I noticed is I can see mailboxes. But then it rained. All of a sudden, the ambient temperature of the mailboxes because of the rain and the ground and everything is the same. So all of a sudden, my super duper little night vision thing is infrared based. I see the people, but I don't see the mailboxes like I used to. Interesting. Limitation of the technology. Because in this case, I only depended on infrared. Right? I mean, it's simple physics. It's not. So that's the kind of things you learn from, and after many years, you say, okay, now that I know that, I need to make sure if I need to worry about that, I have a different thing. I have infrared plus LiDAR. What is the speed of the LiDAR? What is the cost of the LiDAR? Right? So, what's interesting is I was able to find pictures of autonomous vehicles from 1956. Now, there was not very much internet between 56 and 2007, so I was not able to find those. I bet you if I got corporate to come send me some, people have been looking and talking about it. I don't know if has anybody seen the GM video on in 1956, they came out with a movie on what they expected autonomous vehicles to be. It was like this traffic control. It's pretty cool. If you haven't, I think it's on YouTube. It's not what the new autonomous vehicle is going to be, but it's interesting that they were thinking about it way back when. All right? So what this tells us is the OEMs across the board have been thinking about this for a long time, and the capabilities that is being put in are capabilities that have been added over time and have been tested over time, from adaptive cruise, pedestrian detection, automatic braking, collision avoidance, those kinds of things. So Maven, what is Maven? This is our car sharing program, and we do it with Lyft and others, where we make vehicles available to Lyft drivers. So it's a partnership. That's one way. We also do Maven with cities, where we partner with a city. They get Maven car sharing programs, and different cities will have electric cars or different kinds of cars, saying, okay, how can we do car sharing? And you're saying, that's kind of random. Why is this important? What does this have to do with autonomous? Right? I mean, that's the first question. What does car sharing have to do with autonomous? Interesting. Remember the first picture. What did I say? It has a lot of gadgets. What does a lot of gadgets mean? Expensive, right? So how many people have cars here? This is an interactive thing. Everybody. What is your car doing right now? Nothing. Now let's say your car costs $100,000, $200,000, $300,000 of capital. It's depreciating and it's doing nothing. Well, at this current cost structure, and if you want to get more intelligence, you want to make the vehicles better, you need to have fleets of 1,000 vehicles, 5,000 vehicles. I don't care how big of a company you are. 5,000 vehicles sitting around doing nothing that you own, that's kind of expensive, right? So all of a sudden you say, what if I have a fleet of vehicles, and the fleet of vehicles is in a car sharing program, and my utilization rate is 40% instead of 1 or 2%. I think all of us are at the 2% rate, right? At 40%, what is this going to do? This will fund autonomous vehicles. Why is this important to all of us as cities and so on? Because that's the thing, what we need to think of is these kinds of things will this kind of concept, because if the OEMs are saying, we can't even afford that if we don't figure out a self-funding model, maybe this model can help with cities fund vehicle to infrastructure or things like that. Because when we come in and look at these car sharing programs and saying, we need to have a fleet, we need to control the fleet because the technology is complex, we need to fix it ourselves, and we do all this, car sharing pays well, we will use it in a controlled environment within certain city limits, within certain speed limits, and so on. This is a way to be able to have a fleet of 1,000, 5,000, 10,000 in a self-funded model, and that will advance the entire autonomous vehicle. So this is hand in hand. This is not random shotgun approach to why you'll hear GM going in and saying car sharing. It's like, oh, that's completely out of the blue, because it isn't. There's an integration. So if you look at transportation as a service, there's a whole set of things, you know, public transit and so on. But we're only focusing on some of it, right? We're focusing on electrification. Why electrification? Well, a lot of cities that are willing to pay and are interested are big cities, the New Yorks, the Shanghais, the Beijings, and there's pollution. So they're saying, if we're going to do car sharing, we want them to be electric. Okay, so that's one of the criterias, right? You know, autonomous. One of the things is people are saying, you know, what about elder care? You know, I would like people to be able to be taken to the doctors and back. Interesting. Those are the things that's causing people to ask for this kind of help, right? So, telematics, interesting. That's something I'm going to get back to. Here's the beginning of research ideas, right? Has anybody heard of blockchain? Right, blockchain is becoming extremely important. This is the kind of technology, algorithms needed for Bitcoins. Now, you know, the 2-second review of what blockchain is, think of it as a distributed system that, if you want to be a general ledger, think of it as a distributed general ledger, and I'm aware of, and very difficult for me to change everybody in the coin. This coin has been used by who, when, what, and so on, right? So what I'm trying to do in a distributed fashion, instead of going to a master controller, in a distributed fashion, to validate certain things. That's what I care about. So let's say somebody, I need to know the GPS location of the person calling me, say, send me a car. Well, right now we do all this encryption saying, are you who you say you are? Okay, that's good. But I want to make sure your phone is not spoofing a location. I send a car to a location that you're not there. So blockchain, all of a sudden, is important to make sure, where are you? And I need to validate where you are is not being spoofed. Those are things that I know we did not think about till we started dealing with this and finding, you know, you'll get a whole bunch of random calls, people asking you to show up to locations, and they're not where the little device is telling you they are, right? After a while, that can cost you real money, and it can become dangerous, and it can cause issues. So early on, you say, okay, not every single GPS device has this blockchain technology. Maybe is that how we need to make sure it happens? Is that an add-on we need to do? Those are the kinds of things we're looking at researchers to look at. Here's another one, adversarial AI. Has anybody seen this? This is kind of interesting. Here, let's say there's a picture of a panda, right? 57% confidence the AI told me it got trained. Now the same picture, right? We overlay it with this static. And now the AI that's been trained pretty well, 99.3% confidence it's a gibbon. You say, who cares? Why are you showing pictures of monkeys? What if I have something that remember early on I said we needed to add a lot of complexity because visual is not perfect? What if that's a stop sign and somebody figured out to do something? What if somebody sprays the license plate stuff, right? What if somebody sprays hairspray and the reflection changes? Will that change my AI or not? I don't know, because the neural network is kind of complicated. So if I have a stop sign, somebody puts rabbit ears on the side of it, will that change it? Is it going to go from stop sign to something else? Now it's... So the research I need for people to look at is this whole concept of adversarial AI. Because all of a sudden, I'm not only looking at visual, I'm looking at LiDAR, radar. Is it the right height? Is it the right thing? How many people know that certain stop signs, if it's in parking lots, it's certain height, stop signs at different location, different height, so you have to take that into account. There's complexities, right? This field is highly complex and very, very, very immature. So that's why, you know, this whole concept of visual is the, you know, just picking up one method is not, I think, the safest methodology. You know, one of the things I wanted to talk about is non-siloed research. Because if you look at it, encryption is an important thing for us. Blockchain is very important to us. How do I transmit data back and forth? But then let's look at something even simpler. You know, we've been talking about 5G, right? It can be 6G, it can be 10G, right? The amount of data that we transmit is enormous. We're needing to look at compression methodologies. We're looking right now at eigenvalues for correlated data compression. We're looking at self-organizing maps for non-correlated compression. So compression is needed because if you look at the foundation of the amount of data we're going to pull back, that's basic stuff that we need from mathematics departments, statistics departments, those kinds of things. Really quickly, the whole concepts of AI, everybody loves AI. Has anybody knows how hard is it to get training data sets? Very difficult. How about crowdsourcing data sets? Validation of crowdsources data sets, right? Crowdsourcing mappings, crowdsourcing data mappings. What do you mean crowdsourcing mappings? Every car have LiDAR, radar, all this stuff. How can I transmit that data in a compressed fashion and have real-time map creation versus waiting for those fancy cars to run around every few years? Because now every one of the cars is fancy. I'm getting the signs, so those are just a few of ideas of people like us and universities and everybody is looking at, and I just wanted to share a few thoughts. Thank you very much for giving me some of your time. Appreciate it.
Thank you very much for this wonderful perspective. I think we ran out of time, so maybe we won't have questions next.
Yeah. Let's, so we're going to take a break till 10:15. That we'll reconvene. We have last two breakout sessions, one on transportation infrastructure and one on transit. If you're a speaker in those sessions and we don't have your presentation, please head to those rooms and let's get loaded up. And those sessions will start promptly at 10:15.